Up to this point, we've presumed that the state of a system, such as an electron or even a hydrogen atom, can be specified by a function in space and time, that is, the wave function. But perhaps surprisingly, a function just in space and time is simply not enough to describe quantum mechanical particles. We also need to specify amplitudes for the spin of the particle. And the magnitude of this spin is apparently an intrinsic and quite unalterable property of the particle. Spin and its consequences are extremely important in quantum mechanics, and indeed in the everyday practical world. Spin turns out to determine whether more than one particle can occupy a given state. It's therefore crucial to all of chemistry and solid-state physics. Both of these rely heavily on the Pauli exclusion principle that only one electron of a given spin can occupy a given state. Magnetic effects in materials are almost entirely due to spin properties. In optics, electron spin effects are very important in determining polarization selection rules in optical absorption and emission. These polarization selection rules strongly influence the operation of optoelectronic devices such as semiconductor lasers, for example. To see just what the spin angular momentum of an electron is, we can look at how the energies of the electron states, or the positions of the electrons, are influenced by magnetic fields.